So what is a noun? A noun is an atom or a cell. And an atom is defined as a natural number. So 0 would be an atom, 1 would be an atom, 2, 42 is an atom. All natural numbers are considered to be atoms. We also have what is a cell. Now a cell is an ordered pair of nouns. So sort of the simplest cell that we could construct would be 1, 2. You see we use these square brackets to wrap our cells. Now, we can have more complicated cells. Because we said that a cell is actually an ordered pair of nouns, not just an ordered pair of atoms. So we could have, for example, 1, another cell here, 2, 3. This is a perfectly valid cell. Now, taking that example, 1, 2, 3 here, we can actually drop this pair of square brackets here and write it this way. 1, 2, 3. This is just considered to be some syntactic sugar. These two expressions are equivalent, but you will most often see cells written this way. Now, it's important to note that you can't always just simply drop the brackets. For example, if we had a construct that was this way, where the first thing in the head of this cell is itself a cell, you can't drop those brackets, because these two things are not equivalent. Okay? These are equivalent because it's assumed that the tail here, the last thing in the cell, is itself a cell. But that is not the case when we're talking about the head, or the first thing in the cell. Now, one way to think about these cells is actually as a tree structure. So I'm going to go ahead and take the simplest cell here, 1, 2. And then we're going to draw a little diagram here to indicate how this is drawn as a tree. So here we have the root node of the tree, which is actually the entire cell itself. Okay? So then off on one branch, we have the first element, 1, and off on the other branch, we have the second element, which is 2. Okay? We can draw more complicated cells in the same fashion. Let's take a look at the one we were just looking at, 1, 2, 3. And the way that we would draw that is we have our root node. A branch off here with 1, and actually the second element here is the cell of 2 and 3. So I'm going to create another dot here to act as that node. And off of this we have 2 and we have 3. So we could also create, if you wanted, just one more example, a cell that has 1, 2 is the first part, and as the second part, 3, 4. So the way that we would draw this one, we have a branch, and the first thing is itself a cell. So when we branch off that cell, we have 1 and 2. Come back, we branch off of our root node, and we have the second element is again a cell, so we branch off there, 3, and then we branch again, 4. This is how this particular cell would look constructed as a tree. So you may wonder why we are bothering to draw out these little diagrams of these cells as trees. Well, the reason is that there is an addressing scheme that we can use to talk about specific parts of these cells organized in this tree. And the way that that is written out, so we do plus, and then some number, colon, and then we have our cell expression on the other side. Now what's happening here is that this statement, this plus n, is going to be evaluated with respect to the cell expression that we put here. Now later you will learn that everything in Hoon is evaluated against some subject, and in the case of what we're looking at here. The subject that we're evaluating against is the cell. So let's go ahead and take a look at how that numbering scheme actually works. If we take the cell, 1, 2, and we draw that out as a tree, each of these nodes actually has its own index in this system. So let's go ahead and refer to this cell as A for convenience here. So if I do +1 call A, what that's actually going to get us back is the entire cell. So the root node of any cell is 1. So the next node is this one here, and that one's number is 2. And the final node over here, its number is 3. So +2 call A will give us number 1, and +3 call A will give us 2. Let's take a look at another example. If we have the cell 1, 2, 3, we draw that out as a tree. Remember that the second element of this cell is actually itself a cell. 3. So we already learned that this node right here is 1, and that this node right here is 2, and that this one is 3. So in this case, if we did +3, then we say that this is A, +3, call A, is going to give us back the cell 2, 3. Okay? This is where it starts to get a little bit more complicated. The way that this tree addressing, the way that the numbering works here is in level order. So we start with 1 on the first level, and then we proceed to 2 and 3 on the next one. The level after that, if element 2 here is a cell, this becomes 4, this becomes 5, and then these two are on the same level here. So that would become 6, and this would become 7. So the easiest way to actually figure out what the node is going to be is if you have any node n, the head of that node is 2n, and the tail of that node is 2n plus 1. Let's take another example of a more balanced tree. So here we're going to have a cell whose head is itself the cell 1 and 2, and its tail is the cell 3 and 4. So if we draw that out as a tree, we can see 1 and 2 and 3 and 4. So +2, our cell A, maps to this entire cell right here. Okay. So if we number these, this is 1, 2, 3, 4, 5, 6, 7. Now, this is helpful. This diagram is helpful in getting used to figuring these out, but really what you're going to end up doing, if you need to access these things this way, is use the 2n plus 1 formula. If this doesn't immediately make sense to you, don't stress out about it. This is something that will become clear as you use it more. Alright, so here we are in the dojo of our fake Zod that we previously booted. If you don't have a fake Zod, please go back and view the video 0 on how to get a fake Zod running on your system. So here we are in the dojo. So we're going to actually interact with some of these ideas that we've looked at previously. Okay? And we're going to expand on them a little bit. So we said that an atom was one of the natural numbers. So I'm going to go ahead and type in an atom to dojo and see what happens. Okay? So each atom evaluates to itself. Not terribly surprising. Let's try another one. 100. And what if I try 1000? Now I'm trying to type the 0 here, and the dojo is actually preventing me from doing that. Dojo is very opinionated about the way things need to be formatted. It expects the same things. It expects things to be formatted in the same way that they would be in Hoon. And in Hoon, we actually write 1000 like this. Now, you can look at this point here, if you're more familiar with the American Standard Notation, as this is a comma. Okay. Now, a lot of programming languages don't actually use this this sort of notation, but Hoon does, and it strictly enforces it. So anytime you have a number with in decimal with more than 3 digits, you're going to have to add this in here. And as for the reason why this is a dot instead of a comma, it's simply because dots are URL safe, okay, and commas are not. So go ahead and put that in there. We can see that it evaluates to 1000. So, what about cells? We can actually go ahead and write a cell here. 1, 2. Okay, and we can see that again the cell evaluates to itself, which is as expected. So, one thing I would like to point out at this point is that so far we have just been constructing these cells by drawing brackets around numbers, but we actually in Hoon have a number of ways to create cells. One of the most common is the rune here, which is called Kol-Hep. Okay, that's how this rune is pronounced, Kol-Hep. There's an entire document that describes how to pronounce these, so don't stress out about it too much. But this one is Kol-Hep. And we actually give it 2 things to produce a cell for. Okay. Now, you might have noticed that I put 2 spaces here between the Kol-Hep rune and the first number, and 2 spaces between the first number and the second number. Now, the reason for that is that there are 2 kinds of white space in Hoon. And the first one is called a space, which is just a single space. Any larger set of white space in Hoon is referred to as a gap. And you actually have to use gaps to for the spacing between most arguments for the runes. Okay? After you've done this for a little while, that will come easy and it won't be a big problem. Just keep that in the back of your mind for now. So Kol-Hep, this is the way we can construct these runes. So what I'm actually going to do is I'm going to construct a new rune, I'm going to construct a new cell here. 2, 3, 4, 5, and close both of those. So here we see that again this evaluated to itself. One thing you might notice is that this set of enclosing square brackets here was stripped off. That's just syntactic sugar, because this is actually the cell. This outer cell is a cell of 1 and 2, and its tail is this entire part. It just removed those brackets for clarity. All right. So let's go ahead and test out some of our tree addressing. So if I do +1, you see that once again I get the entire thing back. If I do 2, what should I get back here? Okay, so I got back 1 and 2, which is the head of this cell. So if I go ahead and do 3, I should get the tail. If I do 4, I get 1. Okay, if I do 5, that should give me 2. Now, if I do 6, what do you expect to get back? You said the cell of 3 and 4. Good job. If you didn't, that's all right too. Just keep thinking about this stuff. So 5, and here's 7. So now we've reached the point where we said that things got a little bit different. So if I do plus 8 here, we actually get an error. Okay, because there is actually nothing at address 8. However, if we go, if we take a look at where we expect, we want to index into this cell here. Now, we remember that a few minutes ago we noticed that plus 6 was the address for this entire cell. So remember that the formula we said is for the head of a cell, whose value is n, it's 2n to get the head. So 2n, or 2 times 6, in this case, would be 12. Go ahead and do that. You can see that we get 3. And 2n plus 1 was the tail. So there we get our index. So far we have been discussing nouns, which we defined as an atom or a cell. This is actually the data type that comes to us from the lower level language Knock, and it is the only data type that is present in that language. Hoon, however, has a very expressive type system, and let's take a look at some of the things that it can do. The first thing we want to discuss when talking about types in Hoon is auras. Auras are type data on how to interpret one of these nouns that we have had previously. Now, if we take a look at typing 1 into our dojo, we can see that exactly as we expect and exactly as it was before, it evaluates to 1. But we'd like to get a little bit more information about that. So if we use the question mark operator here, now keep in mind that this is a dojo operator. This is not a Hoon operator. This only works in the dojo. If we do question mark 1 here, we can actually interrogate the system about what how it interprets this actual data. So we can see on our second line here, we get pat UD. This is one aura that is available for our use. Now, let's look at a little bit of a more interesting piece of data. By now you have a planet, so you should be familiar with the way that planets are named. So if we take a look at, we can type in the actual, the name of a planet. Here it's actually the name of a galaxy, or the name of a ship, Zod, and we get back Zod. Now, if I type in my planet, rapfyr-diglyt, see that I get that back. Now, I'd like to interrogate this a little bit more about some information about it. So I'm actually going to use this cast operation, which is 2 backticks in front of an expression, and inside those backticks, you are going to put the type you would like to cast to. So what I'm going to do here is I'm going to put pat. And this is actually going to use the aura of noun, or atom, rather. And so we can see that when I do that, I actually, instead of getting back rapfyr-diglyt here, I get this number. 5,374,720. That's actually, as an atom, the name of my planet. So the aura for an planet, our normal names are pat P. Okay. So if I go ahead and type in Zod here, you can see that that's the pat P. Now if I cast that to an aura, we get 0. Excuse me, if I cast that to an atom, we get 0, because that's the actual information. So essentially in this case what we're doing is some stripping away some type information so that we can interrogate what the underlying data is. If we go ahead and do the opposite here, and we give it 0, and we're going to cast this as a pat P, we see that we get Zod back. If I do 1, we get neck. If I do 10, we get sit. If I do 5,000, we get mod res. Now, you should be, some of these will look familiar to you. You can see that we're starting to get into the names of stars here. These 3-letter names are galaxies. And this pat P is a nice illustration of how the auras work. Underneath, the actual data is just represented as this number, but it's presented to us in a way that has some more context around it. So we can tell that this number 5000, when it has this aura applied to it, this pat-p aura, we can actually see that this is not just the number 5000, but is in fact what we're referring to in this case is the name of a star. There are a large number of auras in Hoon that we can use, and we're not going to go through even a fraction of them here. But we will provide... There are links to a more complete documentation on all of the available auras. So one aura in particular that is interesting is a chord. And we type a chord by using single quotation marks and having some text in it. So we can see that when we type that into the dojo just takes that as a chord. It accepts it as a chord. However, if we cast that to an atom, we can actually see here is the full number, that this is the actual underlying data that we're interpreting as a chord for the word hello. We could even cast that into a pat-p and see that we get what is essentially nonsense in this case out, but we're able to transition this data from one type to another pretty seamlessly. So far, the auras we have been discussing have all been applied to atom types. That is, just the single numbers. So we applied the atom aura to Zod, getting us back 0, and we also applied the pat-p aura to the number 10 to get us sit. Now, we also have types that can be applied to cells. And if we actually interrogate a cell that we have built with its information, we can see that it's interpreted now as a cell of pat-ud and pat-ud. One of the useful things we can actually do with cell data is put a specific face on it. Now, a face is similar to a variable name in other languages. Essentially, it's a way to refer to a piece of data that's part of this by a specific name. So we can actually see that we've applied the face I here to the first element of the cell. Now, that's going to allow us to actually refer to that specifically by the name that we gave it. We can actually give face to either side, and there's no limitation in terms of how many characters those can be. So we see we can create my face as the face for the value of 2, and I is the face of the value of 1. We can actually access those the same way we were doing before when we were doing tree addressing. We put the face, we put a colon, and then there's the expression for which we're referring to. Now, oftentimes in the dojo, it's very useful to just set some variable and play around with it. So the way that we actually do that in dojo, again, this is a dojo-specific thing to do. This is not Hoon. This is dojo-specific, is we do the equal sign, and then we give some face. And then we have whatever expression we want to assign. Okay, so now I have this expression assigned to A. So I can then go ahead and say I.A. Now you'll notice that we use the dot here instead of the colon. The dot in this case works. It doesn't work with this previous cell notation, but it is the most common way that you'll see this sort of thing written in actual Hoon code. And the way that you read this is sort of backwards from some other languages you may have encountered, where you put the most general thing first, and then you drill down to the more specific things. In this case, it is the I that is inside of A. That's what we're referring to here. Okay? Where A is the more general case for the entire data structure, and I is something inside that. So one of the major cell types that you're going to encounter in Hoon is a list. A list is an ordered collection of items sharing a type. Strictly speaking, you are able to create lists of items that don't share a type, but for the moment, we're going to pretend that you can't do that. Because in general, you don't actually want to do that. So we create a list using this syntax. So this is actually a list. Now, it's important to note that what makes this a list is the sig at the end. All lists in Hoon are null terminated. This character at the end makes this null terminated. You may occasionally see this syntax as well. That's an equivalent syntax, putting the sig in the front. It just depends. Which one gets used just depends on the context. So lists we're actually able to continue to index into, as we have done previously, in the same ways as a tree. Now, what's interesting here about the list is that you'll notice that when I asked for the second element, I got 1. Or when I asked for plus 2, I got 1. But when I asked for plus 3, I got the cell of 2, 3, sig, or rather the list of 2, 3, sig. So for a list, the head of a list is the first element, and the tail of the list is the rest of the list. Okay. Now, having taken a brief look at lists, we'd like to also take a look at a related data type called a tape. Now, we previously looked at the data type chord, and we were able to cast that into an atom to examine the underlying information contained in that chord. Now, we said that it was very difficult to actually manipulate these because of the fact that it's simply encoded numbers. We, fortunately, though, have a second data type for dealing with strings, and that is the tape. You see that I've used double quotes here instead of single quotes. So that's what makes this one a tape as opposed to this one being a chord. Now, a tape is actually a list of chords where the individual chords are just one character. So since this is a list, we can go ahead and index into it like we have been doing with all of the other cell-based data types that we've looked at. We go ahead and look at 3, and here we see the same sort of pattern where the first thing in the list is the first element, and then the last part of the list, the tail of the list, is the rest of the list. This data type is significantly easier to modify because we have an entire library in the standard Hoon library for manipulating lists, moving elements of them around and removing elements, adding new elements, and so forth. And that makes working with strings significantly easier than it is if you have to work on raw chords. Let's jump back to the whiteboard and take a look at this as a data structure. If we take that tape that we were just looking at, write it out. Remember that we said this was actually a list of chords. So if we deconstruct this as we've been doing before with our other cells, get a tree that looks like this. There's actually one more element over here, which is sig, or the null value that ends all lists. So we can actually show that this is a list by doing a tree indexing. So we have, this is 1, this is 2, this node is 3, then that makes this node 2n, right? So that's 6, that makes this node 7, and its head is at, again, 2n, so 2 times 7, 14, 15, and this is 30, and 31, which makes this node address of 62, this is the address of 63, This node is at the address 126, and this node is at the address 127. Now, as you can see, this sort of becomes a cumbersome method to actually refer to the individual parts. So what's useful is the fact that we are using tapes here instead of chords, is that we could use this, but we also have a whole suite of list manipulation functions that are in the standard library that we can use to modify this. So you actually won't end up using numbers like these usually. You'll end up you'll use other notation to actually index the parts of these.